Hello, this is chapter 3 of CHEM25, and this chapter is going to be about stoichiometry. Alright, so let's see what this is about. We will talk about in what ratios chemicals react, how reactions happen in definite ratios, and how can we use this to calculate quantitative relationship between reactants and products in a chemical reaction. And this is quite fundamental, okay? Because, for example, if you look at internal combustion engine, that you have your car, that we have in some airplanes, you may even have it in your lawnmower or your motorcycle. What we do is we mix gasoline with air, and then they react and form CO2 and water. And then this reaction, there's a lot of heat coming out. It's an exothermic reaction, as we will learn it in chapter 9. What this means is that in order for this reaction to go properly, we need to know what ratios the gasoline and the oxygen react. How much air do we have to plan for the gasoline? And this table, for example, shows here that for various combustive materials, fuels, let's say gasoline, what is the by weight, in what ratio should it react with fuel, and that varies between the various fuels. And this is very important, and you might have noticed that in states that or in areas that lie higher up in the mountains, the fuel composition is actually different from here. Let's say in the Central Valley, we're essentially at main sea level. Or if you happen to have a pilot license, then, on the airplanes, other than there's quite a few knobs. But one of those knobs is the mixture. And the mixture is setting the ratio between the fuel and the air. And the importance of that, of course, is largely a car is always at the same level, so that the pressure and therefore the amount of oxygen doesn't change a lot. But when you go up in an airplane, then you have less and less oxygen. And unless you compensate for that and then put in less and less fuel, the way we say it is going towards more lean. Okay, it's whether lean or rich. You're going towards more lean mixture, you're not getting the maximum heat out of it, and then the engine performance decreases. So there's a little knob on which we set the mixture so that we get the optimal performance, actually slightly below optimal performance for safety reasons when you fly an airplane. Okay, so this is very important. And other things too, if you know, for example, how much fuel your engine uses, you can calculate how much carbon dioxide it emits. And in certain countries, this is mandatory to put on, because of all the hysteria with global warming. So this is a terrific chapter, and this is kind of the very heart of chemistry. So where does all this information come from that we'll need in this chapter? Well, we've covered this, right? So in the previous chapter, we talked about Dalton, Gay-Lussac, Lavoisier, Avogadro, Cannizzaro, and then all this put together gave quantitative information about the atomic masses, right? And then this was mostly over the 19th century. Chemists calculated relative atomic masses. They looked at what proportions the various compounds and elements react. And once we have the relative masses, then we have to decide on what would be our atomic mass unit. And in the modern system, carbon-12 was chosen as a standard. So the mass of carbon-12 is exactly defined to be 12 atomic mass units. It used to be called AMU, and now it's just a U because, there are all these people who, don't do actual work, but they tell others how to call things. And how can you determine atomic masses? You can use a technique called mass spectrometry. And you might have noticed this picture earlier when we talked in chapter 1 about the various subfields of chemistry. This was an illustration for either analytical or physical chemistry. And so in mass spectrometry, what we do is we create ions, and then we determine the mass to charge ratio of ions by flying them through either an electric or a magnetic field, or in some instruments, double focusing instruments, we do both. And in order to make ions, one technique is called electron ionization, or in the old names, electron impact ionization, where we have a high energy electron beam that ionizes an atom and molecule. And so if you take a molecule, high energy electron comes in, and interestingly doesn't create an ion, it kicks out another electron, right, and then creates a cation with it. So this would be the equation for that. This is probably hands down the most powerful technique in analytical chemistry, and it's used in pretty much every lab. The way it works is depicted here, and so we vaporize a sample here on the left. Then these green things it's not a fork, it's actually or a comb. It's the electron beams that intersect the sample and ionize it according to this equation here. And then the ions fly through some accelerating and focusing fields, and they enter a magnetic field. Now, in a magnetic field, because these ions, let's say they all have the same charge, then depending on their mass, the acceleration is going to be different in this direction, and therefore they will be deflected in different amount depending on their mass. And so here we have a deflector plate. In this case, it looks imaging one. It's probably more like you put in slit, right? And then the ions that have a certain mass, they can fly through. And then if you scan with either the magnetic field or better with the acceleration, then you can set which masses of ions will make it through. And then this way you can scan with the mass, and then look at, let's say, certain atom, what kind of isotope masses it has. And so if you look at carbon, for example, then you can see that the ratio between carbon-12 and carbon-13 is roughly about 1. This is the mass you measure is 1.036 times the mass of carbon-12. And so if carbon-12 is defined to be exactly 12, then the mass of carbon-13 can be obtained. But when you look at the periodic table here, right, this is actually circled already. So 12.011, the 12.011 is neither the mass of carbon-12 nor it is carbon-13. So what are these masses here that are listed on the periodic table, right? The rest is less conspicuous, except for if you look at chlorine, it shows 35.45, roughly 35.5. Now that definitely cannot be right. So what's on the periodic table are actually these average masses. Okay, how do you get these average atomic masses? Well, remember that elements in the natural form have various isotopes, and we even saw a video in chapter 2 about the use of these isotope distributions that actually vary from place to place. Not a lot, but a little bit. And so for carbon, for example, you have about 98.9% carbon-12 and about 1.1% carbon-13 and very, very little of carbon-14. And when we do the calculations, then what we'll do is, instead of having to calculate, let's say if I have 15 grams of carbon, calculating that, okay, 98.9% of it will be carbon-12, and then how much is carbon-13, and multiply it and blah, blah, blah. Instead, what we'll do is just use a hypothetical atomic mass for carbon, which is the average of all the isotope, but it's a weighted average. Okay, so we take this weighted average of the isotope masses, and the weight is going to be the proportion by percentage, right? So 12 times 98.9, 13.0033 times 1.1, and then 14.00 times essentially 0. And if you add these three up, Then you get 12.011, which is the weighted average. And from now on, when we make calculations, when we do calculations with carbon, instead of using any of the isotope masses, what we will do is use this average mass. And then, since there are so many atoms, on average, that is really the atomic mass of a carbon. In smaller scale, for example, if you decide how many people are safe to put into an elevator, then you take the average mass of an American, and then that can allow you to calculate how many people can be allowed in an elevator. And then, of course, that average mass is not necessarily the mass of any of the passengers of an elevator, but on average, if we have 10 people, then that would give you a good approximation. Okay, now what's the information that you get out of mass spectrometer? So this is how it will look like. So this is what you scan with, the mass number, and then the intensity is on the y-axis. And so the area under this peak and the area under this peak and the area of that peak will tell you these numbers, what percentage of the various isotopes you have. In this case, you have neon 20, neon 21, and neon 22. And then, if you determine where exactly they lie, you will use, of course, a different kind of mass spectrometer with a higher mass resolution for that. Multiply it with the ratio, then you get the atomic mass of neon. So in this case, what you would do is, what's the example here? So roughly, you would take the mass of the 20, multiply it with 0.9092. Take the mass of the 20, multiply it with 0.00257, and then take the mass of the 22 and then multiply it with 0.0882. Just remember that, 100% is just a fancy way of writing 1, and let's say 2.5% is just a fancy way of writing 0.025. Okay, so don't forget to do that conversion, although your calculator probably will understand percentages in the first place. Okay, now what's the problem with this is that when we look at the mass of the atoms, then this atomic mass unit is very, very, very small. Why? Because the atoms are very small. And so determining how many atoms we have in a sample is just, it would give us very, very large, inconveniently large numbers. So we don't want to do that. What we do instead is we count them by this kind of a dozen, right? We count them by what we call the moles. Now, a good example for something that you've seen already is when you go to the store, right? And you go to the store and your mom tells you to buy eggs. Then you ask how many eggs, and she will not tell you, okay, buy me 18 eggs. She will say, buy 1.5 dozen, or buy 2 dozen eggs, or buy 1 dozen eggs, right? Why? Because eggs are small and they're not bought piece by piece. And so what you do is, since our eggs, the atoms are even smaller, the dozen, right, our dozen, in chemistry, how many dozens of atoms we have, it's not that dozen. Our dozen is very large, and its value is about 6.02 times 10 to the 23rd. This is what we call Avogadro's number. Okay, Avogadro's number. Okay, then how is this defined? Well, it was defined, and I'm stressing the was because, again, those people keep changing things. So it's a number equal to the number of atoms in exactly 12 grams of pure carbon-12. Okay, so what does it mean? Since carbon-12 was defined to be 12 AMU for one carbon atom, then 1 mole of carbon atom is defined to be 12 grams. Okay, and so if you can measure exactly the mass of carbon-12, then you can determine what the Avogadro's number is. Now, this is a very large number, right? What does it mean, 10 to the 23rd, right? It means that 6 and then 23 zeros after it, so not all zeros, but 6.02214085 and then 14 more zeros afterwards. So this is a very large number. And to put this into perspective, if you take a mole of marbles and then distribute it on Earth, it's going to be 15 miles deep. Okay, that's a lot of marbles. Or if you take 1 mole of people, then you can populate 90 trillion Earth-sized planets with it. And my favorite example, and that's why we have this fantastic design for the slide, is if you take 1 mole of M&Ms, that would be enough for the entire population of Earth for 1.3 billion years. So, world hunger is solved. You just need to take 1 mole of M&Ms and then they could feed everyone for that long. Now, of course, you might not get all the proper nutrients, but it would taste good. Okay. Now, in 2019, there was actually a redefinition of the mole. So this is somewhat recent, depending on, of course, when you watch this video, is the previous definition was based on, exactly 12 grams of carbon-12. However, the new 2019 definition, instead of having the mole based on a measurement of a particular isotope of carbon, now they defined it to be exactly this number, right? So it's defined to be exactly 6.022140076 times 10 to the 23rd entities. What are my entities? Well, if I say 1 mole of carbon atoms, this many carbon atoms. If I say 1 mole of electrons, that many electrons. If I say 1 mole of elephants, then it will be 6 times 10 to the 23rd elephants, which is probably more than what we have on the planet. Now, this number is then the fixed numerical value of Avogadro's constant, okay? And the unit would be, 1 over mole. Okay, so if mole is this many particles, then this many particles, 1 over mole is the Avogadro's constant. Now, what we will be using this as is the number n is the number of moles, and then the entity can be anything that we are talking about. This is the old definition here. The atomic mass of carbon-12 is now not exactly 12 AMU and 12 grams, but it's defined, but nevertheless, to quite a few digits, it's the same value. So what we're saying is that if you take 1 mole of aluminum or gold or iron or sulfur, boron or xenon, then they will all contain Avogadro's number of atoms, but the mass of the sample is going to be different. So what would be the molar mass of aluminum? It would be 26.98 grams per mole. For xenon, it would be 131.30 grams per mole of xenon. So 1 mole of anything will have this many particles, depending on how heavy those particles are one by one. That would correspond to this many grams. And then this is a pictorial representation, some of the elements. So what do you think they are? This looks very much like copper, right? What about the middle one? Well, it's obviously mercury. This could be pretty much anything, but by the looks of it, then mostly we see zinc in this form. It's often sold in this form. Now, this one and that one, that could be, this one, maybe it kind of looks like carbon. This could be any of a metal. And then what is this element here? That's kind of easy to see. It's probably sulfur. Okay. So these all represent 1 mole of element, and you can see that depending on their mass and depending on the density, the volumetric amount is different, but any of these contain Avogadro's number of atoms. That's why it's a mole. Okay, so if we do a few sample calculations, but well, you can do either this one. Let's do the second one on aluminum. So we have this very nice aluminum bike frame, which is 2.5 pounds, which is actually a nice frame. How many aluminum atoms does it contain? So how would we calculate that? So I start out with 2.5 pounds of aluminum, right? And let's look up how many pounds is a gram. All right, and then the conversion is 1 gram 1 pound is 453.6. Okay, 453.6 grams. Okay, we convert it to grams of aluminum, and then we know that the atomic weight of aluminum is 27-ish, right? So 26.9815 grams of aluminum is 1 mole of aluminum. Okay, so we cancel out the grams of aluminum, and now we have moles of aluminum. But it asks for how many atoms. And remember, we just have to divide it by Avogadro's number, saying that, or multiply, with 1 mole of particles. Let's say 1 mole of aluminum is this 6.022. Should I write any more digits? 14 times 10 to the 23rd atoms of aluminum, right? And if you multiply it all together, I'll just take the calculator here. So 2.5 times 453.592 divided by 26.9815 multiplied by Avogadro's number 14, right? Then what we get is 2.5 times 10 to the 25th atoms of aluminum. Okay, now one little question here is why did I round it? How many digits? Remember that we have two significant figures in the input number, and therefore we are rounding this number to 2 significant figures as well. Now, this is probably a good place to review significant figures and then rounding and all that. So, how would you calculate then the mass of a mole of a compound, right? Well, we know how to get a mole of an element, right? But what about a compound? It's actually fairly simple, because all you have to realize that, let's say the molecule in this example is ethane, C2H6, which means that 1 molecule of ethane contains 2 carbons and 6 hydrogens. And 1 mole, therefore, contains 2 moles of carbon and 6 moles of hydrogen. And so if you want to know what is the mass of 1 mole of ethane, you take twice the atomic weight of carbon and 6 times that of hydrogen. And then if you add it up, you get 30.070 grams. Okay. Now, how can we do a calculation with it? Let's look at the simplest calculation. How many molecules of this isopentyl acetate is released in a bee sting when one sting will release 1 microgram of this isopentyl acetate? So how do you calculate the molar mass of something more complicated? Now, my very, very strong advice would be, when you calculate the molar mass of something that has several elements, then you start out 17 times the carbon plus 14 times the hydrogen. You look these up from the periodic table. Carbon would be, 12.0107. Hydrogen is 1.00794. Plus 2 times the atomic weight of oxygen, which is 15.9994. And then you add this up. And then what you do is do it reverse. So first you go in this direction, and then you go in that direction. Okay, and the chances that you messed it up both times the same way, it's very small, especially if you don't go back to the same numbers you wrote down, but go back to the periodic table fresh. In those cases, then you probably get it right. You wouldn't believe how many times in a midterm exam the whole problem is solved properly, except that the molar mass is wrong. unfortunately. All right, so let's do this. What would be the molar mass of C17H14O2 if you add it up? And let's do this together. So 17 times 12.0107 and plus 14 times 1.00794 plus how many oxygens? 2 oxygens, so 2 times 15.9994, and then what you get is 250.291. Okay, 2292. Okay, is that correct? 17 looks like. Okay, so how would you do this calculation then? Start out with 1 microgram. Let's say it's 1, so it doesn't convey the number of sig figs. So we don't do any serious rounding at the end. So 1 microgram, not second, sorry. We want to convert it to grams, and so 1 gram is how many micrograms? Remember, micro is 10 to the negative 6, so it's 1 million. Okay, so 1 microgram would be 10 to the negative 6 grams. Okay, and then you get the moles first by realizing that 1 mole of this isopentyl acetate, and just call it IA, is 250 point, let's say round it, 3 grams of isopentyl acetate. Now the grams cancel out the grams and we have moles, and now since it's how many molecules, we multiply this by Avogadro's number, and so that will be 6.022 times 10 to the 23rd per 1 mole of IA. And if you multiply this all together, so then I'll start with 1 microgram divided by 250 times 6.022 times 10 to 23rd, and you get approximately 2.41 times 10 to the 15 molecules of this isopentyl acetate. Okay, so that's a lot, right? So even in a microgram, there's a lot of molecules, because molecules are very small. What about ionic compounds? Because remember, ionic compounds such as sodium chloride, right, they don't have molecules. And so instead of using the mass of a molecule, we use the mass of a formula, and then you can call it molar mass because it's 1 mole of a formula, or sometimes it's called formula weight. What would be the weight of 1 mole of this formula? So for example, calcium chloride here. Calcium chloride, it does not have molecules, right? It has calcium ions and chloride ions, and so one mole of this formula, which would be 1 calcium and 2 chlorides, would be taking the molar mass of calcium, which is 40 point something, and then adding twice the atomic weight of chlorine to it, which then would add up to something like 40 is about 111 grams per mole. Okay, so you take the one for calcium and you take twice the one for calcium, add it up, and then that will give you the formula weight. Okay, now the next topic, and this is going to be the first serious kind of a calculation for us in this chapter, is percent composition. So oftentimes it's useful to know the composition of a compound in terms of the masses of its elements. Why? Because that's what we measure directly, and this is called elemental composition. And in new synthesis research articles, so which means that when let's say an organic chemist makes a new compound or synthesizes a compound that was found in nature, and then wants to show that it's the same one, then what we can do is what they typically do is look at this. This is an actual article from a Journal of Organic Chemistry. Is that the calculated mass percentages are such that you should have 52.31% carbon, 6.86% hydrogen, 3.81% nitrogen, and then when they carried out the measurement, they got numbers that are within the experimental error. So this means that they probably got the compound right. It is indeed the elemental composition. Okay, so how could we do that? Well, let's look at a much simpler one. Let's look at our favorite molecule, well, except for freshmen, of course, ethanol, right? It contains 2 carbons, 6 hydrogens, and 1 oxygen. And if you add it all up, it means that 1 mole of ethanol contains 24.022 grams of carbon, 6.048 grams of hydrogen, and 15.999 grams of oxygen. And then, therefore, if you add these 3 numbers up, the total mass of 1 mole of ethanol is 46.069 grams. Now, how could you calculate the mass percent of carbon? Well, you take the mass of carbon and then divide it with the mass of the whole 1 mole of ethanol. So this 24 goes here, the 46 goes there. And then convert it to percentages, and you get 52.144% carbon, right, in the compound. And similarly, if you take the mass of hydrogen in here, or if you take the mass of the oxygen in here, and then you do the same calculation, keeping this the same, of course, because that's the whole ethanol molecule, well, 1 mole of it, then you get the mass percentages of the oxygen and the hydrogen. Now, of course, since the sum of all of them would be the whole molecule, this means that the sum of the percentages will have to add up to 100%. Now, not always, right? Because we round this, right? So this one, for example, was rounded to 5 sig figs. This is rounded to 4 sig figs. And so where the rounding happens, that digit is actually, it can walk. Let's do an example calculation here. How about the mass percentage of a compound called lysergic acid diethylamide, and this guy is here, the inventor of it. It was a very popular compound in the mid-20th century. And so how would we calculate the mass percentage of the 4 elements, carbon, hydrogen, nitrogen, and oxygen in it? So way to do it, and I just need a fresh green screen for it. So in 1 mole of C20H25N3O, how much carbon we have? Well, we have 20 carbon atoms, so it's 20 times its molar mass, which happens to be 12.0107, and that adds up to 20 times, it's 240 plus 21.4 grams of carbon. Hydrogen, I have 25 of it. Each one is 1.00794 grams, and so that adds up to 25.1985 grams. Next element is nitrogen. I have 3 nitrogens. Each nitrogen is 14.00674 grams. And so 3 times 14.00674, that would, I definitely messed up something here. So 0.0674, that would be 42.0202 grams, and then the last one is oxygen, and I just have 1, so it's a 15.9994, and that is still 15.9994 grams. Okay, so if you add this all up, then let me punch it into the calculator. I get 323.43 3 grams. Okay, let's round it just there. Now, what will be the mass percentages? Then for carbon, the mass percentage is going to be this 240.214 divided by the total molecules, 323.43. And I can just walk back to the numbers, divided by this, and I get 74.27%. All right, and then for carbon, what I would have to do is I would take this number, oops, why did it write? This number, put it in here, and I take the molar mass and then put it in there, right? Or similarly, for nitrogen, I would take this number, take this number, and that would give me the percentage. Okay, and so you can do all that and would get the mass percentages of the elements one by one. Now, this is of course the theoretical part. So how would we go about an actual experiment? So the way it is done is called elemental analysis. And in elemental analysis, it's a process where you take a sample of some material and then it analyzes it for the elemental composition. Okay. And for synthetic chemists, an elemental analysis is sometimes called CHNX. CHNX means carbon, hydrogen, nitrogen, and anything else. Okay, and so the way to do it is you put it in a sample and then burn it in pure oxygen in a furnace, and then you get CO2, water, O2, remaining O2, right, from this, and then other gases. And so what you do is you let it through a water absorber, let's say magnesium, can you name this? Perchlorate, right? Magnesium perchlorate, which will eat out all the water vapor. Then you go through a CO2 absorber, let's say sodium hydroxide, and then whatever is left, use other types of analysis. Now, how would you get the amount of water? Well, you measure the mass increase here. Amount of CO2 would be the mass increase in there. So this is an experimental analysis. And so how would such a calculation look like? So if you have a compound that is made of carbon, hydrogen, and oxygen, and you do elemental analysis, then you start out with this much, 0.2132 grams of this compound, react it with pure oxygen, and then you form 0.426 grams of CO2 and 0.1744 grams of water. What would be the formula? So let's do one of them, okay? So in 100 grams, okay, then you would get 100 divided by 0.2132, right, times that much. Right? If we had 0.213 grams, instead of that, if we analyze 100 grams, then we'll get 100 over that times more. And then we found that we have 4260 grams of carbon, right? So how many grams of carbons would we have in 100? How many grams of CO2 we would have in 100 grams of this sample? So let me put in the numbers, 2132 times 0.4260, and I get 199.8124 grams of carbon, and grams of CO2, right? So from 100 grams of this compound, if we do a combustion in oxygen, then we get this much CO2. And then I want to convert this to moles of carbon in 100 grams. So I take this and then I convert it to moles of the carbon. But first, I would need to convert it to moles of CO2, right? Because I'm going from grams of CO2. And then 1 mole of CO2 happens to be 12.0107 plus 15.9994 times 2, right? That will be 44.009 grams of CO2. And then just to make sure we're all on the same page, we have 1 carbon per mole of CO2. And then if I multiply this together, then I take this divided by that, and that happens to be 4.54 moles of carbon that was in the 100 grams of this compound, right? So this is how such a calculation would go. And you can do it then for the hydrogen, and you can do it for the oxygen, and then those are the numbers that you're supposed to get. Now, once you have that, how would you get the formula, right? Now you know that in 100 grams you have this many moles of carbon and hydrogen and oxygen, but does that tell you how many moles you have in 1 mole? So what you look at is what would be a mole ratio that this corresponds to. So you take the 3 moles and then choose the smallest one and determine the ratio of all the others compared to that. So obviously 2.27 divided by 2.27 is 1, right? So that's 1 to 1. And then the 9.04, that will be 4. So this means you have 4 times as many moles of hydrogen than oxygen. And if you divide the 4.54 that we just calculated here with the 2.7, then you get 2, which means you have 2 times as many moles of carbon than the smallest number was oxygen in this molecule. So the simplest formula you can come up with, and let's call this the empirical formula, is C2H4O, right? For each 1 mole of oxygen, I have 4 hydrogens and 2 carbons. But it doesn't mean that this is the molecular formula, because a molecular formula can be any integer multiple of this. It can be C4H8O2, it could be C54H108O27, or anything else. So what would you need to determine the molecular formula? You would also need the molar mass with this. Okay, so this was the simplest calculation. How to determine the formula? First, the empirical formula for for a compound based on this elementary analysis. Okay, but how do we get the molecular formula again, right? So the simplest formula is C2H4O, okay, that we just determined, but we don't know what would be the molecular formula. Does it correspond to C4H8, or it would be C54, or whatever else? So what we need to have for that is the molecular weight. If the molecular weight is 44, or if the molecular weight is 132, it will be different. So what we need is how many times do we take this formula and can put it into the molecular formula, right? So if, for example, we determine that we need two of these to fit into molecular formula, that formula will be C4H8. The way to do it is simply calculate what would be the empirical formula mass, and then see how many times that empirical formulas will fit into the molecular weight. And so let's calculate the empirical formula mass. So I'm just doing an approximation. I take carbon as 12 plus hydrogen is 1, oxygen is 16. So this is roughly 44. So if the molar mass is 44, then the formula is indeed C2H4O. But what if the molecular weight is 132? And what you have to do is see how many times this 44 fits into the 132. And if I do that, then not surprisingly, I get 3, right? So I take the C2H4O 3 times, that will be C6H12O3, and that will still have the same mass ratios, the same mass percentages, the same mole ratios between the elements, but it will also have the proper molar mass of 132, right? So these are the steps. First, you can determine the empirical formula, and then from the empirical formula, you can get the molecular formula by using the molar mass. So the steps. How to determine the empirical formula first. Okay, so what you do is start out with 100 grams of the compound and then base the calculations on this quantity. Then you determine the moles of each of the elements in 100 grams of the compound. You take these moles, divide each of them with the smallest number so that you get the ratios compared to the element with the smallest number in the molecule. Now, if these are all whole numbers, then we're good. But what if it's not? What if, for example, it was something like C2H5? Okay, C2H5 would be pretty bad, right? Because then you have 2.5 times as many hydrogens. So then you multiply each of these by the same integer so that they're all whole numbers. And we'll see how this goes. And then if you want to get the molecular formula from this, then you can do it 2 ways. Okay, so one is, let's start with the empirical formula, right? So first you determine the empirical formula, and then from that you calculate the empirical formula mass, and then from the empirical formula mass, you see how many times it will fit into the molar mass, and then you take this number and multiply each of the subscript. That's what we did, right? That's how we get the C6 something from the C2. The other method would be, and that's actually quicker, but then you don't get the empirical formula. Instead of using 100 grams, you take the molar mass and determine the mass with the mass percentages of each of the element instead of 100 grams in 1 mole of the compound, okay? And then once you have the masses in 1 mole, then you convert it to a number of moles for each element, and still we're talking about 1 mole of the compound, and so this would directly give you the subscripts in the formula. Now, which one should you use? Well, depends. If I'm asking for the empirical formula, then why don't you just do that and then do these extra steps? But if you want to do everything in 1 step and get the molecular formula, you can just as well do this. All right, let's see a few examples for this. Which one looks more complicated? Well, the second one looks more complicated, okay? So let me write down these numbers so that I can use them. It's a C. Okay, so we have 49.48% carbon, 5.15% of hydrogen, 28.87 for the nitrogen, and we get 16.49% for the oxygen, right? So these are the 4 numbers. And then we also have a molar mass, and the molar mass is 194.2. So what would be the formula for caffeine, right? So let me clear the screen again for this. Okay, and let's start out. And in 100 grams of the compound, this means that I have for carbon 49.48 grams. For hydrogen, I get 5.15 grams. For nitrogen, I get 28.87 grams. And for oxygen, I have 16.49 grams. So what I need to do next is convert it to moles. How many moles of each element do I have here? So I have to divide each one with their atomic weight. And this would be 12.011. This would be 1.0079. This is 14.0067, and this is 15.999. Okay, so this means I'm Now calculating the moles of each element, so 49.84 divided by 12.011, and I get roughly 4.119. Yeah. Then 15.15 divided by 0.9, that would give me 5.11. And then the next one, it's a bit laborious, but not too complicated, 2.061. And then the last one is 16.49 divided by, I'll give you 1.031. Okay, so I have these. This would be how many moles? Okay, let me write it out. Moles of carbon, moles of hydrogen, moles of nitrogen, and moles of oxygen are there in 100 grams. And so I divide all of them with this 1.031. 1.031. Okay, and so this means I'm establishing the ratio of all three of the other elements with respect to the oxygen. And so what I get for carbon, okay, I divide that with that, and I get 3.997. So that's approximately a 4 for hydrogen. Okay. That would give me 4.96. So that's pretty much a 5. For nitrogen, you can see it without a calculator, that would give you a 2. And oxygen is, since it's dividing with itself, then you get 1. So what would be the empirical formula is C4H5N2 But that's not all. What I also want is what would be the molecular formula. So for that, I would have to calculate the formula mass for this. And from the formula mass, see how many times it fits into the molecular mass of 194.2. So I take 4 times carbon, and in this case it's pretty safe just to calculate with the rounded values, because it's got to be pretty close. So this is roughly 97 grams per mole, and then the molar mass was given as 194.2 grams per mole. And so if I take 194 divided by the 97, I get 2, right? So divided by 97, then I get 2, which means I have to take this and then double it. And so then the formula is C8H10 and 4 and O2. And then hopefully this is indeed caffeine, and then we can have our well-earned coffee. Okay, so this is how this goes. You can start out with the calculation of the empirical formula, and from the empirical formula, knowing the molar mass, you get the molecular formula. Now there's another problem here, and that's between phosphorus and oxygen, and I bet that the ratio will have to be P2O5. Okay, so that could be a good homework for you. Again, same way. Take 100 grams of this compound that would contain 43.64 grams of phosphorus and 56.36 grams of oxygen. Take both of them and turn them into moles, and then from the moles you would get their ratio, and then the ratio is probably a 5:2 if I'm correct. And definitely, because it's a white powder, so it's definitely diphosphorus pentoxide, which actually is tetraphosphorus decoxide by the molecule. Okay, so this was the end of our simple calculations that involve no change, right? This was just what's in a molecule from a percentage of masses, how do we get the formula, and so on. But the real meat in this chapter is going to be about chemical reactions and how can we do calculations on it. And so first of all, we would have to learn balancing. You probably, if you've taken a chemistry course before, you know how to do that. And then we can do calculations based on the balanced chemical equation. So our first example is what's depicted here, and then also this is some cool research articles in flame, right? And then there's actually on the right, this is from the cover of Science magazine, which is, one of the hottest journals. And this was done by actually our friends at Sandia National Lab, which is just here in Livermore, 45 minutes from us. And this is a flame which is coupled to mass spectrometer at the Berkeley synchrotron. And then this cone here is used to sample from the flame. So what they're trying to do is understand the flame chemistry, what kind of species there are. But overall, on the whole, what happens is that methane reacts with oxygen, right? Methane reacts with O2, and it forms CO2 and water. And the chemical equation, this is new, right? You've probably never seen a chemical equation before, except, of course, in high school and probably middle school already. So you take methane, which is a reactant on the left-hand side. Another reactant is O2 on the left-hand side, and the products are on the right-hand side, CO2 and water, and they're all connected with an arrow showing which direction the reaction goes. Now, this was an unbalanced equation. What does it mean? That it's not balanced because the number of oxygen and carbon is okay, hydrogen atoms on the two sides are not equal. And the very fundamental principle nature is that mass doesn't get lost, right? So whatever we have on the left in the chemical equation, we have to have it on the right as well. And so if we want to make sure that that is fulfilled, we can balance the equation, right? We can balance the equation by putting numbers in front, okay? Don't balance it by, let's say, scratching out the 2 here and saying that, let's put in a 4. Okay, that's not correct, because you're changing what the chemical species is. The correct way is multiplying how many O2s or how many waters you have in there. And then if you take a look at this, then you'll see that you have how many carbons on the left? 1 carbon, 1 carbon. Okay, how many hydrogens on the left? 1, 2, 3, 4. 1, 2, 3, and 4. How many oxygens? 1, 2, 3, 4. 1, 2, 3, 4. So it's said to be balanced because it contains the same number of atoms of each element on the two sides. And so this is balancing a chemical equation means. And what is a chemical reaction in the first place? What we do is simply take the atoms that are somehow in molecules or sometimes in, not often elements, but let's say if it's a metal, it can be too. We have atoms in some formation on the left, and they are reorganized into products. Bonds are broken and new bonds are formed. And importantly, in a chemical reaction, atoms are never created or destroyed. Okay, you can do that in nuclear physics, but not in chemistry, which means that you have to have the same number on the reactant side as you have on the product side. Everything has to be accounted for. So for example, if you see in this reaction, you probably have, if you go to a Mexican restaurant, for example, and if they bring your fajita in flames, then this is ethyl alcohol, right? This is the alcohol that they put on, and then when they put a match to it, then it will burst out in flames and form CO2, carbon dioxide, and water, right? How would I write this reaction? So this is C2H6O reacting with 3 oxygens, giving you 2 CO2s and 3 waters. So what is the meaning of this? Well, the meaning of a chemical equation is what's involved and then how much. Sometimes I also want to put in the physical states, right? If it's important, whether a substance in a reaction is a solid or a liquid or a gas, they're denoted with S or L or G. And sometimes we have a different letter for those substances that are dissolved in an aqueous solution, that is in a solution that has water as the solvent, and then we use AQ here. Example for that would be, this is actually something that contains all four of them. So you take aqueous hydrogen chloride, which we call hydrochloric acid, and then you put in some solid sodium hydrogen carbonate, or in other words, sodium bicarbonate, and it forms CO2, carbon dioxide. That is a gas, right? You see the bubbles coming out. That's a CO2. Then it forms liquid water, which you have there anyways as the solvent. And then the product is going to be sodium chloride or salt. And then it's aqueous because it stays there dissolved, right? So you have all four of these. You have a solid, you have a liquid, you have a gas, and then you even have ones in the aqueous solution. So how do you interpret this? If I write a reaction, an equation of a reaction, and it is balanced, then it conveys a lot of information. The information, for example, for this reaction, that is again methane, reacting with two oxygens forming one CO2 and two waters, it means that one molecule of methane and two molecules of O2 react to form one molecule of CO2 and two molecules of water. But if one molecule reacts with two molecules, it's also true that 1 mole or 1 dozen will react with 2 moles or 2 dozen, and they will form 1 mole of CO2 and 2 moles of water. Which also means that this many 6 times 10 to the 23rd will react with 2 times 6 times 10 to the 23rd, and then blah 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 on the right hand side. Or I can also say, and this is the important part, this is really for stoichiometry. If I take 16 grams of methane, which corresponds to 1 mole, it will need to react with 2 times 32 grams or 64 grams of O2 to give you 44 grams of CO2 and 2 times 18 grams of water. These two numbers will be for 1 mole of CO2 and then 2 moles of water. It's also true, and then we can check that mass was not lost. If you add up these two numbers, right, you get 80 grams of reactants. If you add up these two numbers, essentially 44 plus 36, you also get 80, right? So from 80 grams to 80 grams, nothing was lost. You can, of course, also check, and we have that the atoms were not lost. So 1 carbon, 4 oxygens, 1, 2, 3, 4 oxygens, and then 4 hydrogens here. 2 times 2 is 4 hydrogens there. So it all checks out. It is a balanced chemical equation from which we get a balanced answer on the grams of the reactants and the products, right? And now just a little sidestep on how would we balance equations. Well, the important thing is you never change the formula, okay? Only the stoichiometric numbers or stoichiometric coefficients that come before them. And the simplest way is trial and error. Do it until you get it right. Now later when we learn about oxidation numbers and stuff, then we'll learn specific techniques for balancing certain kinds of reactions. But overall, what you can do here is first put in a 2 here. Why? Because you had 2 carbons here, but only 1 carbon here. So if you put in this 2, that will fix that problem. So what's the next problem we have? Well, we have a total of 6 hydrogens here, but only 2 hydrogens there. So I will fix that next by putting a 3 here. Right? Now I have 6 hydrogens, and I also have 6 hydrogens here. So that's good. Carbon and hydrogen are balanced. The only thing that is not balanced is oxygen. So how many oxygens do I have on the right? So far I have 7 on the right, but 3 on the left. So I need 4 more, which means I can put a 3 in here, and now I have 6 oxygens plus 1. That's a total of 7 oxygens and 7 on the right. So it's all nicely balanced, and I can write it out. 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens, 7 oxygens, 7 oxygens. Okay, so this would be a good way of balancing equations. Let me show you one more trick, okay? And I'll try to find a good example for that. I would say butane, okay? Butane, C4H10, is also fuel, and it reacts with oxygen the same way. It gives you CO2 and water. Okay, so how would I balance this equation? Well, pretty much the same way. I just take, carbons. I need 4 because I have 4 on the left. I have 10 hydrogens on the left, so I need 10 hydrogens on the right. And then I hit a little bit of a snag, right? Because I have 4 times 2, 8, plus 5, 13 oxygens, right? So that means 13 O's on the right, and I cannot have 13 O's on the left because they come in pairs. So what I do, and I suggest you can try this little trick, you put in 13 halves, right, of O2. 13 halves times 2 would give you the 13 oxygens. So this is kind of balanced, okay? I would say it's balanced-ish, right? Because it has the right coefficient. The ratios are correct. You have the same number of each element on the left and the right, but they're not all integer numbers, so it's still kind of illegal. So what I do, I take this and then multiply by 2. And if I do that, I multiply everything by 2. So I have 2 C4H10s reacting with 13 O2s, going to 8 CO2s and 10 waters. Okay, so this is a neat little trick, especially it applies because a lot of reactions that we do are like that. When it reacts with molecular oxygen and O2, then you don't worry about it too much. You just balance it with half oxygens, and then you multiply it in the end by 2, and then you get it balanced and with integer coefficients. Okay, let's go back. What is then the whole procedure for writing reactions? You determine what the reactants and products are, what state they are in, and then with that you write an unbalanced equation. Okay, and you take the unbalanced equation and then balance it. Now, the best way to do is start with the most complicated molecule, but the least complicated element. What do I mean by that? You start out with the element that only appears in that molecule and one thing on the other side, okay? And then go to the next one and then leave the element, very often it's actually oxygen, that happens to be in various species. And then what do? You check it. Okay, so this is just a take-home advice. Whenever you balance equations, don't just stop with balancing it, also check it. And that's a great thing, because generally when you do a calculation problem, okay, if it's not a multiple choice exam, do you know whether you got it right or not? You don't, right? You kind of hope that you got it right, but you're never entirely sure. But with the balancing problem, you always know. If it balances out, if you have the same number of elements on both sides, you got it right, okay? Now let's try one. Write a balanced equation for ammonium dichromate. Do you remember ammonium dichromate? Is violently decomposing with a flame into chromium 3 oxide, nitrogen gas, and water. So let's start out with ammonium dichromate. Okay, I hope you learned your polyatomic ions. And so it falls apart into chromium 3 oxide. Okay, what's the formula for chromium 3 oxide? It's Cr2O3. Okay, this is, by the way, a type 2. Then I get nitrogen gas, and by nitrogen gas I mean N2, right? Nitrogen comes in pairs just like oxygen or hydrogen or chlorine. And then I also get water. Let's try to balance this equation. And hopefully it's not going to be too complicated. So I have 8 hydrogens on the left, and then I need 8 hydrogens on the right, so I multiply the water by 4. How many nitrogens? It's only on the left in one molecule, and so that would be a 1. Now, do you have to put in the 1? No. If I see that you balance it in writing without the 1 in there, then I take it for right. But if you, let's say if the equation reads like C plus O2 goes to CO2, and you don't put any numbers there, you just leave it like that, I wouldn't know whether you solved it, and that's why it's all 1s, or you didn't even look at it, right? So in that case, in an exam, you should it's 1, 1, and 1. Okay, so coming back here, the nitrogen is fixed, so I need the chromium fixed as well, and so I need 1. So let's see if it adds up. Okay, I have on the left, the only element I have to check is the one that I haven't yet, and it's oxygen. 7 on the left, and then 3 and 4, that's also 7 on the right, so it's neatly balanced. And then this here is actually how it works. You take, and it's actually pretty cool. It's a orange crystalline compound, this ammonium dichromate. You need a pretty high temperature flame to get it started, let's say from a Bunsen burner. And then when it starts, it will sustain itself, and then it looks like a volcano. It's a really, really cool volcano experiment, and it produces a lot of ash, and then the ash of this solid chromium 3 oxide, and it's green. So it looks actually pretty cool because it started out in an orange. You have an orange flame in the center, and then it produces lots and lots of this chromium ash. It's a very fine powder. In fact, I had a friend once who collected coins, and then this was one of the finest and very hard powders you can get, and you can use it to polish. Okay, now let's do some calculations. So now we know how to balance a chemical equation, and we also know what the meaning of it is, right? How it can be used to connect grams of reactants and products. And so what would be the simplest question is, how many grams of oxygen will react with 96.1 grams of propane? So I want the mass of O2 from the grams of the propane. What do I do for it? I use the balanced chemical equation. And from a balanced chemical equation, I can take the following information. I know that 1 mole of propane reacts with 5 moles of oxygen and produces 3 moles of CO2 and 4 moles of water. So from the balanced equation, I can get information between the moles of the propane and then the moles of oxygen. So what would I do? I will convert this to moles of the propane. Right? I will convert this to the moles of the O2, and I will convert that to the grams of the O2. Okay, this is, by the way, a propane tank here. Okay, so how would I do that? Okay, I would need the formula mass of propane, right? Because that's the information I need to convert the grams of propane to moles of propane. So for the moles of propane, I get to the mass of propane, and in this case, I divide by 44.1, and I get the moles of propane. Then I look at the balanced equation, right? I get, well, that's a different question. We're trying to answer the CO2. So from 1 mole of propane, I get 3 moles of CO2, right? So I take this mole ratio and then convert it to moles of the CO2. And very importantly, the stoichiometric information is between the moles. Moles of propane, in this case, moles of CO2. And then having the molar mass of CO2, by the way, that's just a coincidence at both 44, I would get the mass of the carbon dioxide. Okay, and if I want the oxygen instead, what mass of oxygen does it react with? Then the steps are pretty much the same. Now I get the moles, how many moles of oxygen that reacts with, and then what will be the mass of such oxygen. Okay, now let's write this out before we go into any more complicated problems. How would this look like? And I have a little space in here. How would you actually carry out this calculation on a piece of paper? So C3H8. And let's use this entire thing as one long conversion. Okay, so I do one conversion between grams of propane and the moles of propane. Then the next conversion is going to be between moles of propane and then the moles of what I want. Let's do it in oxygen, right? In this case here, right? And then I want to get the grams of oxygen. So from the moles of the O2, I want to get the grams of the O2. So let's put in the factors. Well, I know that 1 mole of propane happens to be 44.1 grams of propane. And I also know that 1 mole of propane reacts with 5 moles of O2. That was from the chemical equation, right? This 5 here. And then I know that 1 mole of O2 molecule is roughly 32.0 grams of O2. And if I multiply this all together, and that's the beauty of it, that you don't have to stop after each step, you just use this as one long snake of a calculation, and then what you get in the end is that right? 348, and I get 3 sig figs, so 0.7. Let's round it to 3 sig figs, so 349 grams of O2. Okay, that's what it reacts with. Very good. Okay, so this is the steps. Again, you just treat it as one long conversion, converting from mass to moles, moles to the moles of something else, and then the moles back to the grams of what you want in the end. Okay, let's see again. Balance the equation. Okay, then convert the mass to moles, use the stoichiometric numbers from a balanced equation to set up the mole ratios, calculate the moles of the desired reactant and product. It can be anything. It can be between a reactant and reactant, or a reactant and a product, or it can be product to reactant or product to product. And then once you have the target moles, you convert it back to mass, right? 1, 2, and 3. Where do all these come from? This is the molar mass, this is another molar mass, and then this is the ratio that is coming, the mole ratio that is coming from the balanced chemical equation. Okay, so let's see this in an example. Okay, we have 2 antacids. One would be baking soda, and then the other one would be milk of magnesium. Let's see if we remember these ancient names. And it's used to neutralize hydrochloric acid. And the question is, which one is more effective per gram, right? How would you express that? Well, how much HCl is neutralized per gram of the antacids? Okay, so we need a few numbers for that. And we start out with 1 gram of both. And let's write an equation. Oopsie. How do I do that? No, come on. Okay, there it is. Okay, so let's start with, what was it? Baking soda. Okay, baking soda is sodium hydrogen carbonate. React with HCl and then forms sodium chloride, and then it bubbles because of the CO2 that goes away. Now, luckily, this is balanced right away, 1 to 1. What about the other reaction? It was milk of magnesia. Milk of magnesia is magnesium hydroxide. And again, this is type 1, so I didn't have to say how many or what's the charge. It's just magnesium hydroxide. It reacts with HCl as well, and then forms magnesium chloride, and then water, and then CO2 the same way. However, this doesn't seem balanced because we have 2 chlorines on the right, 1 chlorine on the left. So I would have to multiply this by 2. That takes care of the chlorines. But now, what's wrong here? Okay. The CO2 was just... Okay, forget about that. Okay, so what's wrong here? I have 1, 2 plus 2, that's 4 hydrogens on the left, and then only 2 on the right. So I have to multiply this by 2, and that takes care of the oxygens. And I have 2 oxygens on the left, 2 oxygens on the right. Very good. So I have both equations, and I have the mole ratios. And so I would want to start with, let's say, 1.0 grams of sodium bicarbonate. I convert to moles of bicarbonate by using the 88.0066 grams of sodium hydrogen carbonate per mole of sodium hydrogen carbonate. They react 1 to 1 with HCl, right? This is a 1 and then this is a 1. So 1 mole, wow, this is long writing out the bicarbonate. So now I have converted it from gram to mole and from mole to the moles of the HCl. And in the end, I don't need to get the grams here because it just asks for which one is more. So if I do that calculation, let's say 1 divided by 88.0066 times 1, that's an easy one. So I would get 3.96 moles of HCl. Good. Now, what about the other ones? 1.0 grams of milk of magnesia. And then let's convert it to moles of the magnesium hydroxide. And then 1 mole happens to be 58.3197 grams of magnesium hydroxide. And then the mole ratio here is different, right? It's 2 per 1, right? So you get 2 moles. Well, you react with 2 moles of HCl for each 1 mole of magnesium hydroxide. If you do the calculation, well, you can kind of already tell, right? Because not only does it react with twice as many HCl's, but it's also lighter than the other one. Then what did I... Okay, then the first calculation was off. Okay, let me see. So this is 0.0343 moles of HCl. This was something wrong. Let me type it in again. Oh, because I left in that 96. Oh, God. Okay, so let's redo that. Why did I get such awful numbers? Oh, because this is a different calculation. Okay, so let's do it again. So 1 divided by 88.0066, essentially. Okay, good. So it's 0.0114 moles of HCl. Okay, so sorry about that one. I don't know what my calculator was doing. And so one reacts with 0.0114 moles and the other reacts with 0.034 moles. And if I close this, then that's indeed the numbers we should have gotten, at least after a while. Okay, nice. Now, what's next? Well, so far, the calculation in the first place, let's go back to that actually. So here in this, what mass of, let's say this one, what mass of carbon dioxide used by this mass of propane? But this assumes that the propane has all the necessary amount of oxygen available. Now we actually calculate how much of this is. It has more than 340 something grams of oxygen available. What if it doesn't? What if the amount of available oxygen limits it? A simple example, you take a glass jar, put in a candle, okay, and then it has some oxygen from the air. But if it's closed, you can kind of see that unless it's a very, very small candle, it's not going to be the wick that limits the amount that can burn, but it's going to be the amount of oxygen, right? And so that leads us to the concept of limiting reactant. So a limiting reactant is the reactant that limits how much products you can get, okay? And for that, when you take chemicals and then mix them together for a reaction, if you mix them in stoichiometric quantities, that is, it's the right number of moles for the reactants to react with each other, which means that will be used up all at the same time. Okay. Now, what if, for example, if you're making hydrogen from methane and water at high temperatures, what happens is, what's the reaction? Let's try to come up with it. CH4 plus water, it goes to hydrogen gas plus carbon monoxide, and then to balance it we need this. Okay, so if I want to get how much water is needed to react with this many kilograms of methane, then if you take the grams, convert it to moles, converted to moles of this, converted to grams, then you would realize that this many kilograms of water is needed. Okay, but what if you take this many kilograms of methane and then mix it with 3 tons, so 3.00 times 10 to the third kilograms of water? It means that you have too much water, you have it in excess. That is, the methane will get consumed first, but then water remains in excess. And that means methane is the limiting reactant because the water will run out first before the methane is run out. So if you want to do a stoichiometry calculation in which you get the amount of 2 reactants, then first you need to determine which reactant is limiting. That's what the limiting reactant problems are about. And then obviously, this is something that we'll do in the exam. In fact, most stoichiometry problems shall be like that. So another very important process is between nitrogen and hydrogen forming ammonia. The mole ratios are 1 to 3 to 2. And that means that 1 molecule of N2 will react with 3 molecules of hydrogen, giving you 2 molecules of ammonia. But what if we mix, instead of the 1 to 3 ratio, we mix them in a 5 to 9 molar ratio? To visualize that, I have 1, 2, 3, 4, 5 nitrogens and 9 hydrogens. And we know that each one nitrogen will react with 3 hydrogens. So this will be one such reaction, another one, and then the third one. And then all the 9 hydrogens are used up, but only 3 of the nitrogens. So we're left with an excess of 2 nitrogens. So on the product side, you'll see that those 2 nitrogens are left over. They're in excess, okay? And then since from 1 nitrogen and 3 hydrogens you get 2 ammonias, each of these little circles contain 2 ammonias. So we're left with 6 ammonias and then 2 leftover nitrogens. So who's the limiting reactant here? Well, always one is in excess and the other one is limiting. So the hydrogen, okay, in this case the hydrogen is limiting and the nitrogen is in excess. Okay, now how do we do that? Then we're a little bit more complicated when we don't start out with a certain number of moles, but we start out with a certain mass. So let's say if we react 25.0 kilos of nitrogen with 5 kilos of hydrogen, what would be the which one would be the limiting reactant? And then starting from the limiting reactant, let's try to determine how much product we would form. Okay, so for that I need a blank screen again, and I start out with 25.0 kilograms of nitrogen, okay, and then 5.00 kilograms of hydrogen. And what I want to do is calculate how much product I got from each, and whichever gives the smaller amount of products, that would be the limiting one, and the other one is in excess. So first of all, let's not forget that we're talking kilograms here. So 1 kilogram is 1,000 grams in both cases, right? 1 kilogram is 1,000 grams. So this first step is just because we started with kilos. And then I want to convert the grams of nitrogen. And the grams of nitrogen is 1 mole of nitrogen happens to be 28.013 grams of nitrogen. roughly. I didn't use a calculator for that, so you can check my work. And then 1 mole of hydrogen happens to be 2.016 grams of hydrogen, again without a calculator, so you might want to check. And then the question is, how much ammonia do I get, right? So the stoichiometry part here is, remember, we got 2 moles of ammonia for each 1 mole of nitrogen, and we get the same 2 moles of ammonia, but from 3 moles of H2. Okay, if you were to forget, the reaction looks like this, N2 plus 3 hydrogens going to 2 ammonias. Okay, so we're getting there. We now have the moles of ammonia, and then we convert that 1 mole of ammonia, and then for that I will actually use a calculator. So 14.006 plus 1.007 times 3, right? That will be 17.0306 grams of ammonia. And then this is the same here, just don't like writing it out. So let's start with the first one. So 25 times 1,000 divided by 28.13, I hope, times 2 times 17.0306. Okay, and that gives me 30.4 kilograms. Okay, it gave me 30,400, and I converted it on the fly to kilograms, which, you know, is 1,000. What about 5 kilos of hydrogen? Okay, and that would give me 28.2 kilograms of ammonia in both cases. So which one's limiting? Well, the limiting is the one that gives less, which is a hydrogen, and the other one is the one in excess. And then using X for the excess is actually pretty good, because then it crosses out that line and you know that it's not the calculation you should do. And so the answer would be 28.2 kilograms of ammonia. Very good. Okay, so let's go back to the slide. So the answer was, we calculated first the moles, used the mole ratio, and then limiting reactant happened to be the hydrogen, and then the calculation that started with the limiting reactant, that was the one that determines how much product is formed. And then for home, let's do a similar one. Is nitrogen gas is made from reacting gaseous ammonia with copper oxide, copper 2 oxide, by the way, this is a type 2. Okay, at high temperatures, how many grams of nitrogen will be formed? So let me just write down the reaction for you. It's actually pretty typical. What happens is you're withdrawing the hydrogen with the help of oxygen from an oxide. And so ammonia plus, 3, not ammonium, oh my god, copper oxide, right, copper 2 oxide, it would be 1 to 1, right, because the oxide and ion is 2 minus, copper 2 plus is 2 plus, right, and then that would give you nitrogen. What else would it give you? Well, it actually give you copper metal, it would give you water, right, because the oxygen in the copper oxide is one that takes the hydrogen out. And so if I want to balance it, and I really don't, but let's do it. So 2 ammonias will give you 1 N2, and that's taken care of, but then you will need 3 waters on the right, which would mean you need 3 oxygens. Luckily, this is not an O2, so you can go 3. And so you have 3 coppers. Then let's fix the copper here. Okay, so this will be the balanced equation. And if you look at all the elements, it should be all right. Okay, so this will be a typical limiting reaction. And there's plenty of such examples at the end of the chapter. So I urge you very, very much, not just to stop at these examples, but just do a bunch of problems from the end of the chapter on limiting reactants. The simplest way, and there are many other ways, you can go ahead and compare, for example, the moles of the 2 reactants and then compare it to the mole ratios to determine which one's the limiting, which one's the excess. But the safest way is just calculate the products from both reactants, whichever gives you the fewer products, the less products, that will be the limiting one, that will determine the actual reaction. That's what you have to use, and the other one is the one that is in excess. Okay. Now, there's one more thing that we need to cover here, and that is realizing that it's chemical reactions, just like us, they're not perfect. So sometimes there are side reactions, sometimes we're not doing it right, and therefore we don't always get 100% out of this. Just like when one of my daughters, let's say, makes cupcakes or cookies, then if we're planning for 2 dozens of cookies, sometimes you don't get a whole 2 dozen. Sometimes simply because another sister comes by and then she eats one of these cookies, or when you put the cookie down and it breaks, right? So maybe not 100% of the cookies that you're planning for will you actually get, but you get a less than 100% yield. Okay, so yield is the amount of product that's actually obtained in a chemical reaction. Now, yield means, it doesn't mean, whether it's the actual one or expressed in percentages. It just means how much you got. The theoretical yield is the one that, as its name says, that you should get in theory. Okay, the amount that is formed, that is the amount when the limiting reactant is totally used up, and that's how you calculate the theoretical yield. That's what we've been doing. Okay, I gave you the reactants, you choose which one was limiting, you calculate how much product you would get from that, and that would give you the theoretical yield. Did you actually do the experiment? No, you didn't. That's why we call it theoretical. Now, the actual yield is if you carry out the experiment, how much product is actually formed in the actual reaction. And I said actually like 3 times in this sentence. It just means that if you actually bake the cookies, how many cookies did you really get? Which is not necessarily the theory. You should have gotten more cookies, but then you didn't. And so the 2 can be related. Which one is smaller? The actual yield is smaller, right, than the theoretical yield, unless you were cheating. And so the percent yield or the relative yield expresses the ratio of the 2. You should take the actual yield and divide it with the theoretical yield, and that will give you the percent yield or relative yield. If it's expressed in percentages, which just means 0.01 would be 1%, then we call it the percent yield. So learn this formula. And then if you ever forget, remember that the percent yield is somewhere between 0 and 1, 0 representing when nothing happened. Okay, let's say you couldn't turn on the oven. 100% means you had no losses, and then you got exactly what theory told you. And so typically it's in between the 2. Sometimes it's actually very, very close. Like say for a titration reaction, which we'll learn about later, titration reaction need 100%, otherwise you cannot use it for quantitative purposes. One of the reactions we can do in my research lab is we can make peptide chains. It's a biomolecular, whatever. And then it goes in discrete steps in an automatic synthesizer. It's like a little robot. And there, those reactions are optimized to go with very, very high yield, very high percentage. Otherwise, if you're making a long chain, then after a while, it's going to be a very low yield. Okay, and And so in these cases, what you have to do is then once you get the theoretical yield, then multiply it with the percent yield to get the actual yield. And so the general scheme for solving stoichiometry problems starting with mass is that, of course, you write an equation, balance the equation, and then convert masses to moles, determine which one is limiting, which reactant is limiting, and then use the amount of the limiting to tell the moles of the products. Typically, these two should be done in the same step. You just calculate the amount of product from both of them, and then whichever is smaller was the limiting one. And then in the end, you convert the moles to mass if that was the question. That's what you want to do. And then this is really in the very heart of chemistry, right? When you write a chemical reaction and then from the balanced chemical equation, you get quantitative ratios between the reactants and products, or reactants and products. So my advice here is don't stop with the lecture. First, let's do all the problems that were in the lecture slides, and some of them I actually did for you. So check that you did them correctly, and then start working on problems from the end of the chapter. There are plenty of stoichiometry examples, and also theoretically you can use any formula in those mass percentage examples. So start practicing your calculations. And this was chapter 3. And thank you so much. And then see you soon in chapter 4.